Uh, Hello, this is Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Yiannis Vlassopoulos from the Athena Research Center, who will tell us about mathematical game theoretic approach to understanding neural nets. As I always do, I'll watch the chat, and if you have a question you're not sure about asking, put it in the chat, and I'll reply if it's easy, or we can raise it if it's a good question. And of course, there'll be a chance for questions and discussion at the end. So with that, Yiannis, please.
Thank you very much. So first, I'd like to thank Mike Douglas for inviting me. It's great to be with you. And so what I want to talk about is basically some effort trying to understand what is the mathematical structure hidden behind neural networks, and in particular, ReLU neural networks, which are some of the most commonly used. So trying to, let me see if I can get this. Yeah, okay, perfect. Yeah, so basically the idea is that, trying to stop thinking about neural networks as black boxes, that you just sort of, have an input and an output, but you have no idea about, what's going on inside, what is the mathematical structure underlying them. So we tried to do this for the ReLU neural networks. So what we came up with is basically that actually you can interpret ReLU neural networks as a kind of game. In particular, a zero-sum turn-based stopping game, optimal stopping game. And then you can show that the output of every neuron is actually the value of the game at the corresponding state of the game. So that buys you some stuff. I mean, you construct the structure as usual, in mathematics. Then you construct some sort of, enveloping complicated structure, but then you are able to prove things that you wouldn't be able to prove before. So I will show you a couple of things in that direction. Output neuron given bounds on the input. Then there is a sort of path integral formula that expresses the value of the output of every neuron, in particular the output of the outgoing neurons. Then you can relate. It could be interesting to also see what is the continuous analog of that. That basically is differential game theory and something called the Hamilton-Jacobi-Isaacs equation, which is generalization of control theory, where you have two agents. And then there's some relation with logic, something called game semantics. This is some of the stuff. So this is joint work with Stéphane Gobert, and you can find the paper in the archive. It was posted maybe a month and a half ago. All right, so let me first start about reminding everybody what ReLU networks are. So basically, you have a usual neural network with L layers, capital L layers, and layer little l has KL neurons, let's say. So and then we have the weight matrices WL, and bias vectors BL, and the input vector is let's call it X. Now, one thing that is particular about this setup, but this is just for convenience, we decide to number the layers from the bottom of the neural network. So the first layer is at the bottom, and the last layer is at the top. And that is because the game actually that realizes this, the value of the output of the neural network is not played in the direction of the game, it's played in the opposite direction. And actually what happens is that the Shapley-Bellman recursion, which is a backwards recursion, is the one that produces the ReLU network. Okay, so besides that, everything is completely standard. So the only thing you have to keep in mind is that, just the numbering of the layers is, the last layer is the first one, and the first layer of the neural network is the capital L, the last one. And recall that, ReLU function is just psi of x equals max of 0, x. It's applied coordinate y some vectors, and then we define the affine map WLV plus BL. And then the total output function that the net is computing is just basically a composition of ALs with psis. You apply the affine map, then you hit with ReLU, then apply the affine map, ReLU, and so on, all the way down. And so this is what we want to understand. We want to understand what this map really is computing. Now, the starting point is we wanted to have something maybe like a probabilistic interpretation. But the problem you run into immediately when you try to make probability interpretation is that the weights are not necessarily positive. So, the natural thing to do is to try to take this weight matrix and split it into positive and negative parts. So when I say positive and negative part, let's call the positive part of a number the maximum of 0, comma a, and the negative part of the number the maximum of 0, comma minus a. So for example, the positive part of 2 is 2, and the negative part of 2 is 0, and the positive part of minus 2 is 0, and the negative part of minus 2 is 2. So both positive and negative parts are always positive numbers, and the number is positive part minus its negative part. So of course we can take this matrix W that's hitting some vector y, and we can write it as the difference of the positive and negative parts, and then we can write it as W plus y plus W minus y. Now the question is how to rewrite everything, basically sort of using this observation and constructing a probabilistic theory out of this whole story, which is what we're going to do actually. Okay, so to do that, first what I'm going to do is I'm going to remind everybody a few things about zero-sum games, and then I'm going to define what the game is. The game is defined precisely by just using basically all the data of the neural network. So what are zero-sum games? Zero-sum games, I mean, maybe people are more familiar with Markov decision processes because they're basically used in reinforcement learning. So when you do reinforcement learning, you have states, you have actions, you have probability distribution, transition probabilities from state to state given an action, and you have some reward and things like that. More general, so MDPs, Markov decision processes, are basically games with one player. Only one player acts. Now we want to have two players, and basically this is going to reflect the fact that the one player is going to maximize and the other player is going to minimize. And so we just copy everything that we do in Markov decision processes. And so we have a set of states. We have the set of actions that you can take at this state. You have the probabilities, the transition probabilities from state given some action. You have the reward R. You have some discount factor, which is basically what's going to be. The discount factor is just because these weight matrices are not, so the sum of their row elements do not sum to 1. So we're going to have to normalize them. That's going to be some normalization element. Pi denotes the final payoff, the final reward, and capital T denotes the number of stages of the game. So how many stages you have to play. Okay, yeah. So for example, chess could be an example, right? So a state is basically just a particular configuration of the chessboard with all the pieces on it, and the two players play. And in the chess game, actually something interesting happens. And you don't get a payoff during the game. You only get a payoff at the end of the game. So at the end of the game, if you win, you get 1. If you lose, you get -1. And if it's draw, you get 0. Each player gets 0. So there are games that the only reward you get is at the end of the game. But there are other games when you can get rewarded at every stage of this game that you're playing. And our game is going to be like that. Actually, what's going to happen is that the bias is going to be, as I said, we're going to use the weights to define the probabilities, transition probabilities, and we're going to use the biases to define the rewards. Okay, so we have a finite set of states, and the A1 of S is the actions that we have at any state, and where the first player, the player max, player 1 is trying to maximize, so we'll call him max. Player 2 is trying to minimize the reward, and we'll call him min. And there's a bunch of actions. Now, in our game, it's going to be very simple because it's going to be a stopping game. So the only action that the player will have, the only choice the player will have is either to continue or stop the game. So I'm giving you a preview of what's going to happen. We have this secretly, basically what's happening when you do this game theory is that you consider basically game trajectories. And you also need the notion of a policy. A policy means that for every state, the policy tells you how to act. And if you have this policy, then what you can do is you can write a measure on the paths. That's the idea. It's just basically path integrals. For every path, you get a probability and you get a reward. And that's what it's really constructing. I'm saying this because, there's a lot of notation here. but it's important to keep the geometric picture of just the game trajectories. Every game trajectory has a probability associated to it, and you have the rewards. And a game trajectory is a trajectory where the players, not the same player always plays, of course. The players change by some rule. And one player is trying to maximize the reward, and the other player is trying to minimize reward. So basically, we have this probabilities of transitioning. If you're at the state S, and you take action A1 and A2 to go to a state S prime, there's a probability of transitioning. Then there's a state T reward of player max. And because it's a zero-sum game, whatever the max guy gets, the min guy gets minus of that. So that it's a zero-sum game. Okay, the total reward is always zero. Now, a randomized, as I was saying before, a policy basically tells you at every state which action to take. And there are two kinds of policies. One is randomized, where you find the probability distribution over possible actions. That's what this pi here is. For every S, it gives you basically an element in the simplex, which means it's a probability distribution. But actually, for the ReLU, we're just going to use deterministic. So it's not going to be probability of stopping or continuing. It's going to be either stop or continue. And actually, this is going to give a Boolean flavor to this whole thing because it's 0-1 choice. Either you're going to stop or you're going to continue. It's 0-1. Okay, so this is what a policy is, very important. We have the deterministic and randomized policies. And now let's come to the game trajectory. This is what I was talking about, a game trajectory. Game trajectory means that you start at some state ST, and then you take, both players play, A1T, A2T, there's some actions. And this gives you the probability of choosing the next state. You choose the next state, ST plus 1, and blah, 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 and so on. So you get this whole path. And then there's the associated reward. So you accumulate rewards as you go from state to state. And then there is this discount factor, the product of gammas is just discount factors. And you accumulate more and more discount as you go further and further away from your starting position, which is S little t in this particular case. So basically, you do get a probability measure on game trajectories. If you have a sequence of randomized policies, so our game is going to be very simple. It's going to be just on just going to be, there's no loops. You cannot go back. And it's going to be a directed acyclic graph. And you have many stages. You have T stages, let's say. So basically, you can find the probability of the whole trajectory if you know what the states and the actions are. You just multiply the probabilities, and this gives you probability of a trajectory. And now you also have, so remember we also had the reward. So now we just take, so the value with respect to this particular policies is just the expectation value of rewards with respect to this particular policies. So basically you just sum up probability of every path times the reward of the path. And you sum over all paths, and that's the value given these particular states. Now, that is a kind of linear problem for the moment. Now, the nonlinearity comes because actually, so there's one more thing to say about this. The fundamental equation underlying this is the Kolmogorov backwards recursion, which just tells you that these expectation values are related to each other. And basically the relation is that, you can, if you are at one particular state, you can separate going one state forward and everything else. So the expectation value given some policies pi and sigma at time t is the expectation value of all policies at exactly at the state S prime, which is the next state that you go after S. So you have this VT plus 1 with the same policies, and you take the expectation value, multiply with the probability to go to this S prime, and you add over all the S primes. And so this is a recursion relation. It's a backward recursion relation. Okay. This is called the Kolmogorov backward recursion. Now, the problem becomes nonlinear because what we're actually interested in is not just the values for individual policies, but we want to maximize over the maximizer and minimize over the minimizer for the values of all given policies. And that actually is the value of the game. So this value of the game is basically what's called a Nash equilibrium. And if it's realized by some optimal policies, which we call in here pi star and sigma star. And the basic idea of what is this max min is that, if you're, as you can see here, if you're at VT pi star sigma star, if you change your sigma star, you become bigger. So the sigma guy is the minimizer, so he doesn't want to become bigger. So it gets worse for him if you go from sigma star to anything else. And if you go from pi star to anything else, it becomes smaller, which is bad for the maximizer. So neither of them has an incentive to do anything when you're at that point. It's the best they can get for both of them. And actually, this now you have to prove that this saddle point, Nash equilibrium exists, and that was proven by Shapley. And all these things sort of generalize basically the Bellman equation that you have in the Markov decision process. You should always think that if you only have one player, so if you only have pi or only have sigma, if you only have pi, then everything becomes just a Markov decision process. And then basically you get an equation on this. You get a recursion on this by using the Bellman optimality principle. So this is what the value of the game is. And the fundamental equation is called the Shapley-Bellman equation, which basically, just like the backwards Kolmogorov recursion, was an affine relation that would move you backwards in time from one moment to previous one. Here, you're actually using the optimal policy value. So this is the value of the game. And basically, this is what generalizes the Bellman optimality principle. In the optimality principle of Bellman, if you have just max, you say if you have an optimal solution, then every part of it is going to be also optimal. Because if it were not optimal, then you could make this better, and then you can make the whole solution better. So then you can actually generalize this to this max min case. So this is the Shapley-Bellman equation. And it tells you basically that if you want the value at state S, you can write it as max min over all next values. And you have the value at the next time slot. And you take basically it's just the Kolmogorov equation, but now you have the max min. It's exactly the same thing, but now you have the max min on it. Okay, so the Kolmogorov equation, you can think of it as basically the expectation value by the condition. So if you take expectation value, you can write it as expectation value of expectation value, because you condition on the next step. And this Shapley-Bellman equation is just the same thing, but now you also add the max min, and Shapley proved that it still holds. And if you only have max or only have min, it reduces precisely the Bellman equation, which is also a backward recursion. And this has a boundary. The boundary condition is the final reward. So these are discrete versions of differential equations. There's the Hamilton-Jacobi-Bellman equation. There's something called the Hamilton-Jacobi-Isaacs equation. And these are sort of the discrete versions of that. Okay, so now we're going to simplify our life a little bit, because we're going to be in a turn-based game, which means that not at every state only one player plays. And the state knows about this. So the state will tell you which player plays at that state. So we split up the states into S1 and S2. There's the states where the maximizer plays at S1 and the minimizer plays at S2. Yeah. So basically, so that's what a turns-based game is. And now we can take this previous equation that we had with the max min, and it breaks up into two pieces. It breaks up into two pieces. One with just has because the state actually is the maximum. Let's say the state belongs to the maximizer. He only wants to maximize. All the state belongs to the minimizer. They only want to minimize. But that doesn't mean that these equations are coupled, because if you look at VTS, for example, it's a function of VT plus 1s prime. This VT plus 1s prime could belong to the minimizer. So they're not independent. These are two coupled equations. So they look precisely like the Bellman equations, but they're coupled. One for the minimizer, and it would be a Bellman equation for a max problem and a Bellman equation for a min problem, but these equations are actually coupled. Okay, So we're going to use exactly these equations. So now we're going to simplify our life a little much, very much, because we're going to see concretely what all these things mean. And basically the idea is that this ReLU, which is a max between two actions, one action is going to be stop, the other is continue. It's going to be precisely the max that we get here, and it's going to be another min. That's why we're going to have to enlarge the space of states a little bit. Okay, so and let me also note that you can also find that you can do an argmax, and you can find what the optimal policy is. The optimal policy is important because if you have the optimal policy, then remember that fixing a policy linearizes your picture. Then you just have a path integral to solve. So the optimal policy is just the argmax of the value. So which is the action that maximizes this particular value, and we can compute this also in the ReLU case. So let's now, so after this general excursion, let's now apply this to our ReLU net game. So the ReLU net game is going to be a game which is we're going to construct given a ReLU net. The ReLU net has all its weights, has its biases, has everything, all the information about it. And now we're going to construct a game. The game, and recall always that we count the layers from the bottom up. So the first layer is the bottom layer of the neural network. So the game is going to be played in the opposite direction that the neural network is running. Okay, one player is trying to maximize reward and the other player is trying to minimize reward. But what is reward and what are the states? So, okay, so actually one more thing is that the input to the neural net will be the terminal reward of the game. So the terminal reward of the game will be the input to the neural net, some vector x. And the output of the ReLU net is going to be the value of the game at the outgoing corresponding states that I will show you what they are right now. Okay, so basically there's exactly as many time stages as there are layers of this neural network. And note that the Shapley-Bellman equation that we discussed before will be a backward recursion. So the Shapley-Bellman equation will be actually from the top of the neural network to the bottom, and the Shapley-Bellman recursion will be precisely the ReLU activation function. That's how we're going to set this thing up. Okay. So basically, let's introduce some notation. So let's say we're in layer little l, and we have neuron I in that layer. Let's call it L comma I. Now, this neuron is going to give rise to two states. One state is Li plus, on which the maximizer plays, and one state is Li minus, on which the minimizer plays. So, and then we stop again. What is inquiry? Well, the way we incarnate that is we say there's a so-called cemetery state. Cemetery state means that when you go there, you stay there forever and you don't get any reward. So that's what a cemetery state is. These are the states of the game. So once you have your neural network, the states of the game are just double the neurons. Every neuron gives rise to a max state and a min state. Okay, so I'm going to show you a picture in a little while so you can get the sort of geometric picture of what this is. Now, what is the reward? If you're at the Li plus state, the reward is just a bias. And if you're at the Li minus state, the reward is minus the bias of the corresponding neuron. The terminal reward also, so remember we have double the number of neurons. So the positive terminal neurons get the input to the ReLU net, so the xi's, and the negative ones get minus the xi's. And the discount factor is just basically the normalization factor. So gamma IL is just the sum of the absolute values of the WLIJ. We're going to use just to make probabilities. Okay, so the action, as I said, is basically there's only two actions. Either you move on, so you can only move from one layer to the next layer. You're going up the network from its end to its beginning. And you cannot jump. We're just taking a very simple, the simplest possible case. We cannot jump. You just go to the next. You can go to the next layer, but with a certain probability. And what is the probability? Well, that's what we're going to define now using the weights. So the probability to go from if you're at stage L and you're at I plus, you can go to J plus with probability WIJ plus divided by gamma I. So the the positive part of wij gives you the probability to go from I plus to j plus, or if you're at I minus to j minus, it's the same probability. So basically the idea is that if you have a positive weight, this keeps the same player playing. If the max player plays, then they keep playing. If the min player plays, then they keep playing. If the weight is negative, then the player changes. And that's why, you have PL I plus J minus. In other words, the probability to go from Li plus to Lj minus, or the probability to go from Li minus to Lj plus is WLij, the negative part of that. Okay, these are both the negative and positive part are positive numbers. We scale them so that they add up to 1, and we use them in that way to create probabilities. So now you can start moving around. These are all the probabilities. And then you can, this is just checks that this normalization works exactly as we want. That if you start at I plus, you can go to any j plus or any j minus. And the probabilities for going to either one of those, they add up to 1. It's very important to always normalize the probabilities, because that's how you get the connection with paths. Actually, when you try to work all this out, you see that the only thing to make this thing actually a path integral, depending on paths, you need to normalize your probabilities. So we keep all the probabilities normalized. And this is just what I was saying. This is what I was saying before, that if the weight between two neurons is positive, then you go from I plus to j plus, or from I minus to j minus. And if the weight is negative, then you go from I plus to j minus, or from I minus to j plus. So that's how the game works. Okay, so now we have encoded everything. Let's also introduce a notation for the policy. So we said the policy just at every state will tell you what to do. And it's deterministic. So it will not give you any probabilities. It will just say stop or continue. So basically, it's just a pattern, a Boolean pattern on every neuron, or on every state actually of the game. Remember, the states of the game are twice the number of neurons, because every neuron gives rise to two states: one for the maximizer, one for the minimizer. Okay, so we have these patterns also, and here's a picture of what's going on. So you can see that the ReLU net is running downwards. You can see that arrow on the left of the picture, and the ReLU net game is running upwards. So any game trajectory will start from the bottom and will keep going up. Now, in this picture, what do all this means? The dark dots are the max states, the maximizer plays there, and the white squares are the min states. The minimizer plays on the white squares. So and then we're assuming there is a policy. The policy is denoted by this pattern of 0 and 1s. So on the left of every state, you will find a 0 or 1, and you have to abide by that. If it's a 0, you have to stop. If it's a 1, you have to move. So for example, if you look at the first column, it keeps finding 1s, and then there's a 0, but it avoids that 0 by going to another 1, and it makes it all the way to the top. Some other trajectories never make it to the top because they just find some 0 in the middle of their trajectory. So these are the trajectories, and then you can see actually the terminal reward, the input to the net is some vector x, which is here has 8 components, x1 up to x8. You have to input that as a terminal reward on the positive, on the max states, and as and minus that on the negative min states. So that's how this game is played. It's a little bit like you can think of it as a chessboard when you have the black and white squares, the max and the min squares, and then every time you move, you collect a reward. Because remember that if you're in a max state, you collect the bias, and if you're in min state, minus the bias. Okay, so that's the picture you should keep in mind. And we're going to come to this picture again later. So now we're going to write what the Shapley-Bellman equation is for this ReLU net game. So it simplifies very much, because so we have this ReLU net. It has some input x, and these are the values at the different states. And remember what the Shapley-Bellman equation tells you. It tells you basically you have to maximize overall actions. Well, actions are just two. Either go to cemetery or keep going. If you go to cemetery, you get zero. So that's the zero comes from. If you go to the next state, then you have to take the average over all possible places you can go. And if you're an Li plus, you have to go to either to L plus one J plus or N plus one J minus. And when you go there, there's different probabilities. So these are the probabilities that are weighting these values. This is precisely the backward recursion. So you have the value of the game at the next state waiting for you there. And that's how you backtrack. And the boundary condition, the terminal condition, this is basically just the fact that the value at the end is going to be xi or minus xi, depending on if you're in a max state or a min state. So that's what the ReLU is actually. And you already can see this happening here. Well, let me move on. Yeah. Okay. So this is the theorem. The first theorem is basically precisely that if you have a ReLU net and the input is x, we're going to tell you, this is going to tell you the output of every single neuron, and the output of every single neuron, not just the last row, every single neuron. The output of that neuron is going to be the value. Well, I mean, if you look at the max state, the corresponding max state, it's going to be the value of that max state. It's going to be equal to the output of that particular neuron. And if you look at the min state, it's going to be minus the output of that particular neuron. So every output of every neuron is interpreted in this way as the value of that particular game at some state. Okay, so then we're going to see now in a little bit why this actually is useful. But basically, that's how we interpret it. And I want to show you a little bit of the proof because it's really elementary. Once you get over all the notation, if someone is not used with the notation, but basically it's just by induction. So this is true at the end, at the terminal reward, because at the terminal reward, the value of the game is the terminal reward. So that's what it means. VLI plus X is XI, VLI minus X is minus XI. And then you assume that the output of the J neuron is equal to the value at the J neuron L plus one state. And then we're going to show that at the L state, you get also the output of the neuron being the value. Oops, okay. So, and everything is basically set up so that this works. And the proof is very simple because we just look at the Shapley-Bellman recursion. So you get the max of this comma that expression. But that expression, once you realize that this is Vj plus and Vj minus are just the outputs of the corresponding neurons, one of them is Yj and the other one is minus Yj, the probabilities are cooked up precisely by being the positive and negative part of the weights. So when you rewrite this, you just get the positive part minus the negative part. And the positive part minus the negative part is that number. Okay, if I take the positive part minus the negative part, I get the number Wij. So this is just precisely the ReLU. This is just precisely, sorry. So this is precisely tells you that this is the ReLU output. So the ReLU output is nothing else but just the Shapley-Bellman equation for this particular game. Okay. All right. So one may think like, why make your life so complicated? Well, now we can actually think about the problem instead of just having an infinite amount of multiplications, additions, and maxima to take, or a very big amount. So one thing that we can use the fact that, well, actually, let me point something out. In fact, actually, the way we define the game, and let me go back to the game picture. Here's the game picture. As you can see, the terminal rewards are basically xi and minus xi. That's when this gives you the output of the ReLU net. But nobody's stopping us from taking different terminal rewards. We can take A1 up to A8 for the max guy. We can take, B1 up to B8 for the min guy. And this is still perfectly well-defined game. So the game is more general. It's doubling the number of states. It's more general, and it agrees with the ReLU net precisely when this AB inputs at the end, the terminal rewards become x and minus x. Okay, so now let me make another observation. The map from value to value at different states is called the Shapley operator. When you look at the Shapley-Bellman equation, you find VL as a function of VL plus 1. This is precisely the definition of the Shapley operator. Now, the Shapley operator is defined by positive matrices because all the probability matrices are positive, and everything else respects the coordinate-wise order. So there's a coordinate-wise order. Let's go here. So if you consider, if you just think of Rn with a coordinate-wise order, which means that if you have a vector x and a vector y, to say that, I mean, this is a partial order, not everything is comparable to everything else, but if x is less than or equal to y, it means that x1 is less than y1, x2 is less than y2, that xn is less than yn. Okay, this is the coordinate-wise order. And now we can look at the positive operators, the operators that respect that order, that are monotonic with respect to this order. And actually, the Shapley operator is monotonic with respect to this order because it's defined by positive matrices with positive elements. And then, all the other addition, subtraction, min, max, or multiplying by a positive number, they all respect this coordinate-wise order. So the Shapley operator respects the coordinate-wise order. So how can we use that? Well, we can try to find bounds. So in other words, let's say that the input x that we put into the ReLU net is between some vectors a and b. This is what I was saying before. Yeah, so this is just the observation that basically let's call the value of the big game v bar, and the value of the game that when we have just the input x or x and minus x, let's call it just v as we have been calling it already. So this is telling you that v bar of x minus x is just v of x, which is the output of the neuron. Okay, but now let's consider the more general game, and let's say that we have in this coordinate-wise partial order, let's say we have some interval bounds. In other words, let's say that the input x is between some other vectors a and b, which means that coordinate-wise, the vectors of the coordinates of a are less than the corresponding coordinates of x, and those are less than the corresponding coordinates of b. Of course, then we can say that minus x is between minus b and minus a. So the vector x minus x is between a minus b and b minus a. And now we know that the Shapley map for this extended game is order preserving. And therefore, the value at a comma minus b is going to be less than or equal to the value at x comma minus x, less than or equal to the value at b minus a. In other words, because this in the middle here is just the value, this is just the output of the neural network at the corresponding state. It tells us that the output of the corresponding neuron is going to be between these two values of this Shapley game, the Shapley operator, the values of this extended game. So basically, we have a way to propagate bounds for any neuron. If we have some bounds for the input, we can propagate bounds for any neuron of this neural network. Now, that's nice, but one may ask the question, like, how good are these bounds? I'm not sure how good these bounds are. We haven't made any experiments. That's something to do, but probably we can improve on the bounds even better. I mean, it turns out that for those of you, I mean, this actually turns out to be related to something called static analysis of programs, where you have a big program and you want to control the interval of any variable in that program. And there's something called abstract interpretation, which turns out to be related to this. And it's possible to, instead of taking just intervals, take more complicated shapes like polyhedra and so on. And this is possible that this will give even better bounds. But we do get these bounds. Yeah.
Yiannis,
Yeah.
Yeah, so does this extended game have a simple expression in terms of the actual function that it computes, like
Yeah,
generalizing? Yeah, what is
it's
it?
just the same. It's the same thing as the Bellman equation. You just use the Bellman equation, but now instead of having x and minus x, you have
Yeah, I
a and
see.
b.
You could work it out. You could work it
Yeah.
out. I mean, did you work it out? I mean, is it some simple extension of the ReLU network?
I didn't work it out any further than just looking at the fact that we can write the Bellman equation
Okay,
for it, the
I was
Shapley-Bellman equation.
curious to know what it is.
Yeah,
Okay, keep going.
yeah. Okay, thanks. All right. Okay. Now that's the first step. That's the first thing we can get out of this. Another thing we can get out of this is we can get an expression of the output of the neural network as a path integral. Now, thinking about this, it's kind of like very natural to want to do that. A path integral is just really just I mean, the most basic thing is just the product of matrices. When you multiply matrices, we're essentially doing a path integral. And we have these matrices, maybe we can do something like that. And actually, we can, and it's actually interesting. The result is interesting, what comes out. So the basic observation is that this ReLU computes the value, which means the optimal value, which corresponds to the optimal policy. Now, in this particular case, it's very easy to compute the optimal policy. Remember that at some point we had this slide where we were saying that the optimal policy is given by an argmax. You take an argmax. You take the action. You find the action that maximizes the value at any given state. And when you do this very simple calculation, which is really just elementary, and you can see it in the paper, you get out precisely that the optimal policy is precisely what the ReLU gives you. In other words, the optimal policy is to continue if the ReLU output is positive number, and if the ReLU output is zero because this quantity is going to be negative, then this is the optimal thing is to stop. So basically, what does the optimal thing tells you? It tells you you have to take a decision if you continue or not. If you can somehow estimate the average, the expectation value of what are the gains you're going to have if you continue, and actually it's going to be less than zero, then you say, okay, well, it's better for me now to stop because I don't have to gain anything if I continue. And vice versa, of course, for the minimizer. So actually, when you find all the gates, all the Boolean gates for all the ReLUs, if the output is 0 or 1, that is the policy of the maximizer, and the exact opposite is the policy of the minimizer. So if the optimizer had better go, the minimizer had better stop, and vice versa. So now um, so now, so now we can go back because we're playing with two different things here. One is the Shapley-Bellman equation, which is a nonlinear object, and the other thing is the Backlog-Kolmogorov. Well, I mean, so we just have the fact that the value given policies is precisely a path integral. Therefore, now we have the optimal policies. Therefore, if we compute this path integral for the optimal policies, then we should get the optimal value, and that will be the output of the neural net. So all we have to do now is just go and implement the optimal policy, and this will give us precisely a path integral computing the output of this network. And this is what this slide is saying. It's saying basically that the output of the network is the value corresponding to this pi star and sigma star, which are the optimal policies. And this, once you fix the policy, it becomes a linear problem. It's just the expectation value of the accumulated rewards. Just really, literally, the probability, the sum over all game trajectories, the probability of a trajectory times the reward. Okay, so here's the same picture again, but now we can interpret it in a different way. Let's say that this policy is not just an arbitrary policy. This policy is the optimal policy. So when you take basically, if I want to find the output of any neuron, in particular the ones which are the output of the neural network, all I have to do is just take all game trajectories that start from there and follow them. Follow the optimal policy. The optimal policy tells me what to do. I know what the optimal policy is, and follow it, and then accumulate some rewards, calculate what the probability is, multiply the probability by the rewards, and do this for all paths that start at my particular point. Now, one interesting thing to observe is that not all paths make it to the top. So the paths that don't make it to the top, they're indifferent to what the terminal reward is, to what the input to the neural network is. So actually, they don't care. So they're not part of the calculation. I don't know what that means really, but they kind of coincide. I mean, maybe we can leverage to understand something about how the information is flowing in this neural network. But it's kind of the same neurons that I think they're called dead neurons when you do the training and notice that the backpropagation, so the game is going in the direction of the backpropagation. And we're not talking about training the network at all. We're just talking about a given ReLU network, but the game is going precisely in the direction of the backpropagation if we were training the ReLU net. And when you're training this in the backpropagation, if there is a ReLU which is 0, then it stops changing, called these dead neurons. These particular neurons here, they kind of stop the paths. And now the interesting thing is that every input to the neural network determines a pattern, a Boolean pattern. So it's like, I don't know, I mean, it looks a little bit physicsy to me, that you have some sort of, I don't know, spins or something, and they can be up or down. And then you put the boundary condition, and this fixes a pattern. And then you're computing a path integral where you make this kind of random walk with rewards. And maybe the rewards can be thought of as energy. And that's what it is. So that's a way to think about what the outcome of the neural network is. Now, one final thing about the story is that we can kind of leverage this to get a little bit of the beginning of a logical picture, because when we ask the question, where's the logic? How's the logic incorporated in ReLU nets? I mean, ReLU nets are not really used as language models, of course. They're used as classifiers, but still, they're definitely. I mean, you have classes. You want to classify the images. There's definitely ways you can think about implication, which is the main property of logic. Let me just try to make a very simple observation. Let's say we have just one single output neuron. And let's say we use this neuron to separate between images. The images come in as this vectors x. So every time the vector x is inputted, which is now we know the terminal reward of the game, the input to the neural net, the output is some number. Let's say there's some threshold, and if that number is greater than a, then it's a cat, and if it's less than a, then it's not a cat. So how can we interpret this using the fact that this computes the value of a game? Well, actually, the value corresponding to the optimal policy, as I was saying, the optimal policy is really a saddle point in the space of policies. If you move sigma a little bit, you're going to become bigger, which is what sigma doesn't want. If you move pi a little bit, you're going to become smaller, which is what pi doesn't want. So that's why you balance at this Nash equilibrium. But now we can sort of have a logic interpretation of this. We can say that, let's say actually we find any policy pi such that with respect to this policy and to the optimal sigma policy, the value is greater than a. So it's classified as, so then it's actually classified as a cat, because that value is smaller than or equal to if we take the value with the optimal max policy pi star. So therefore, the value, this guarantee for us that this is in the category cat. So we can re-express this in the following way, that there is a policy pi such that for any policy sigma, the value of pi sigma is greater than or equal to a. So this has a kind of flavor of logic. And the same thing, vice versa, is if it's not a cat, there is a sigma such that for every pi, this value is less than or equal to a. There's something called game semantics. And basically, I don't know much about it, but this is one thing that one could look at. Game semantics treats logic as a game And when you have an expression, one guy is the maximizer, the other is the minimizer, one takes the OR operator, one takes the AND operator. You construct an expression, and then if the expression is true, the maximizer wins. If the expression is false, the minimizer wins. And here you have something similar with thresholds. Instead of just 0 and 1, instead of true and false, you have something with actual values. And you may try to extend this to the case where you have many outputs, and then you have many categories, and you have, you take like the argmax, determines like which one is the biggest output, determine what category it is, and try to think if there's a similar explanation. But thinking about this in the opposite way, you can also think of it this as somehow, you have some input, and the output is like, let's say we have two neurons, one for cat and another for dogs, and you can kind of separate. You have the cat game and you have the dog game. The cat game is given by orbital trajectories that are starting from the cat neuron, and it goes up and it meets the terminal reward at the end, which is the pixel, which is the image, the pixels of the image that we have plugged in. And the dog game does the same thing. And then, if the value is bigger than the cat, for the cat and the dog, then you say it's a cat or vice versa. So this is kind of reverses the image that we have of nets, in the sense that it's the output that is trying to evaluate the input by playing this game. Okay, all right. So this is as much as I'm going to say about the ReLU network. But now that I have a few more minutes, we can try to also see how this extends, because it's very natural to try to just to see what happens when you smooth it out. When you smooth out the ReLU function, in particular in the most obvious way, in the best possible way, which is just to use what's called the Softplus function. In other words, if you define like the activation function psi tau, which is tau, you can think of this as a temperature, and then you have log of 1. 1 really is e to the 0 plus e to the x over tau. And the limit as tau goes to 0 is precisely the ReLU function. And we're going to see that this actually is a special case of a very general result. So the question is, so obviously we can replace the ReLU function and with this Softplus function. We get a different activation, and we get this smooth activation function. The question then is can this also be interpreted as a game? And the answer is yes. And it's almost the same game as for the ReLU, except that now we have to take the same probabilities, transition probabilities of states, the same states, but the difference is going to be, it's still an optimal stopping game. In other words, the choices are just stop or go on. But now the policy is going to be randomized. So you're going to stop or keep going or continue with a certain probability. And the reward will have, to the reward, we will add the logarithm of the policy probability. This is called the entropic regularization of the game. So it turns out that if you do this modification of the reward by adding the logarithm of the probability of the policy probability, then you get precisely the game for the Softplus neural network. So let me just walk you through just a little bit of that. Show you just what the basic idea is. So again, we have layers. We just number them as before from the end of the neural network to the beginning of the neural network. And now we just have to compute this function. So we just replace the psi, which was the ReLU function, with this psi t, which is the Softplus function. And the basic trick of the game is the Legendre transform, the Legendre-Fresnel transform of the entropy is the free energy. That's what we have to use basically. So this is sort of well known in physics, obviously, here, I mean, in statistical mechanics, I mean, it just tells you that if you have a system with the energies are minus qi, tau is the temperature, and h is well, I mean, for us it's the Shannon entropy, but if you take the Gibbs distribution, then it would be the Gibbs entropy. But basically, this is the identity you need So that's all you need to be able to generalize the previous discussion to this discussion. And the maximum here is realized by the Gibbs distribution. That distribution is going to rise also at the policy. And then, when you take the limit as tau goes to 0, this collapses and you get the maximum of the QIs. All right, and we have the minimum and the minimum version of that. So we keep all the same states, the initial probabilities, terminal reward, and we modify only the state action rewards. How? Exactly this way. Before we had little r was the reward at state Li plus, and it was the bias. Here we're adding up minus log probability of the policy. And this is for the continue action. And for the stop action, we had like no reward before, but now we're going to add some reward, which is going to be the log probability of the stopping action. So this is just very small distributions, just a couple, they just have two numbers, p and 1 minus p. And so the claim is that if we define the rewards by using this entropic regularization, then we get exactly what we want. We can write down basically, we write down this. This is just all notation here from here on. This is the value at the next stage. You can write down the Shapley-Bellman equation, the expected reward for continuing. One comes from this Q, which is what we had previously. Another part comes from this probability, from this logarithm of the policy. And the expected reward for stopping is this. And then you write down the Shapley-Bellman equation. Sorry, I'm going through fast now because we're kind of running out of time. But if you want to see the details, you can see it in the paper. But basically, the idea is that when you write everything down, you end up with the Shapley-Bellman equation, which is precisely the Lozano transform that we were talking about before. The idea is that because you've added these logarithms of policies, basically what you add is the Shannon entropy of the policy. And so what you have is the Shannon entropy of the policy and just this Q. So applying this Lozano differential transform that we had before, we end up precisely with the fact that the value is the log of 1 plus e to this Q. And the optimal distribution that we had before now becomes a Gibbs distribution. So this is the probability, yeah. This is the probability, and the other part is just 1 minus that. And then you have another theorem. Yeah, you have this is the same thing, but for the min version. And then finally, we have another theorem which tells you exactly the same thing, but for the Softplus networks. So in other words, if you replace the ReLU activation with this Softplus activation, then the output of any neuron is going to be, so you have this twice the number of states. So for every neuron Li, the output is going to be the value of the game at Li plus or minus the value of the game at Li minus. So yeah, and okay, I think I'm going to stop here. We're really running out of time.
Okay, very good. Thanks.
Thank you.
Do we have questions from the audience? You can just speak up, or you can put it in the chat. I mean, if nobody has a question, I'll ask questions. So I mean, I think this is quite interesting. I mean, you've connected to two subjects that people, I never heard the idea that there would be such a connection. So that's quite interesting. And on the other hand, I don't know that much about. I mean, I know the definitions of game theory, but not the methods. And it does seem to me that the network you started with is a much simpler thing than the general game in the class that you're talking about. The network's just a function, and a game is a more complicated thing. Right?
Yeah, but I mean,
but which means that one, I mean, maybe one could turn it around and learn things about those games, that you could do something like this and turn them into functions and neural networks and things.
It's very possible. Yeah, I mean, yeah, I mean that's an interesting thing. I mean, so basically using this makes the problem of training this neural net an inverse game problem. We're trying to find the game
Well, did you
that
try,
reproduces them.
you didn't talk about training, so training would be
No, I
changing the
didn't.
ways.
No, I didn't. We haven't
So
we haven't thought about
do
it
you have a
yet.
game
That's,
theory picture of training? Because there is like evolutionary game theory.
no, I don't. We haven't had
Okay.
the chance to think about it. That's one of the things that we want to think about,
Okay,
definitely.
okay, maybe that will
But
work.
one thing that may be along the lines that you're suggesting is, I was thinking that if you do reinforcement learning, in reinforcement learning, you basically, I think, use the neural network as a black box to compute the policy.
Yeah, right.
But now the policy can be also incorporated in the whole structure, because the reinforcement learning is basically an MDP, and so now you have this game inside this MDP. So maybe you can sort of have a better understanding of reinforcement
Well,
learning
I
this
mean,
way.
another question, which I'm only going to ask kind of vaguely, but maybe it will make sense to you, is that your games in general involve probabilities for transitions, and so then suppose you didn't have, I mean, your players can kind of optimize the whole thing, but suppose they can only sample to evaluate the game, right? So instead of knowing a probability, you just sample. So there's usually some sense in which with enough samples you do converge on the original thing, right? You could estimate all the probabilities and you would get the optimal strategy, right? So is there some statement like that here where
You're
once you
talking
train the
about
network?
training?
No,
Talking
I'm
about
still
the
not
training
talking.
part?
I'm not yet talking about training. I'm talking about what you formulated. But I'm saying suppose the players don't
Yeah.
know the probabilities. They only sample and get
Well, the
samples.
probabilities are absolutely defined by the weights.
Well, for sure, but you can still postulate a player, an agent that doesn't know them.
Yeah, that's why I said it kind of sounds like training. So in other words, you're
But
trying
it's
to
not. But
find
it's
what the
not. I mean, you could also add the idea of training, but you can postulate that independently. You can just say, I have an agent which wants to optimize, but has to, learn. Has to estimate, the probabilities. I mean, it might turn out to be related to training in some way, but the way I'm saying it isn't in itself.
yeah.
And then
Well, I
you would
mean,
have to ask the question of, well, how quickly do they learn? How quickly do you get this?
yeah, I
And
mean,
again, I'm just trying to broaden your connection because
yeah,
now that you have this relation to games, the game is a very much more general thing than the original network. Like
yeah,
you had this extended thing, but there's just so many generalizations it could have, and that's maybe the
yeah.
focal.
Game theory has a lot of methods about policy iteration and value iteration and things like that.
Right, right.
And we could probably use that here. And
Yeah,
I think the bound estimate of the input given the output can be generalized much more using this kind of methods.
Okay.
But we haven't had. But that's there's a lot of projects that we want
Yeah, sure.
to
Okay.
do, but we haven't
Okay.
had time to do them yet.
Right. Thanks. Are there more questions from the audience? Well, if not, let's thank Yiannis for a very intriguing talk and explanation. And next week, I think we'll have Courtney Paquette from McGill talking about the theory of machine learning again. So hope to see you all there.
Okay. All right. Thank you very much.
Thanks,
Thank you very much, Mike. Thank you. Thanks, everybody.
Okay. See you soon.
Bye-bye.
You. Bye-bye.